Here's an example of what we call coffee cup calorimetry using just like an insulative styrofoam cup with a lid. So read the question and then pause this and write down the equation that you plan to use.
So hopefully you wrote Q is equal to MC delta T. If you look back at the question, there's a lot of information about the aluminum. There's also some information about the water. So we know the mass of aluminum here. We know the initial temperature of the aluminum. Now remember what your delta T means. Your delta T means final minus initial temperature. So it's okay if you get a negative value there. Sometimes you'll also get a positive. You do have the mass of the water, but we're not going to worry about that now. And then it says the final temperature in the calorimeter is 26.5 degrees Celsius. So that's actually going to serve as your final temperature for both the aluminum and the water. The ultimate question is the initial temperature of the water. So right now, it appears here that we have 4 variables, but actually since it's final minus initial temperature, there are 5. So we know 4 of the 5 of those for the aluminum because we also have the specific heat of the aluminum. So if we have the mass of the aluminum, the specific heat of the aluminum, the delta T of the aluminum, we can solve for the heat, either lost or gained, of the aluminum. And to figure out if heat is lost or gained, look at your delta T. So your delta T here is going to be final, which is 26.5 degrees Celsius minus initial 98 degrees Celsius. So that's going to give you a negative value for your delta T. So that means you're also going to get a negative value for your Q, which just means that heat is released. So plug these numbers in and see what value you get for Q. So hopefully you got an answer here of negative 1,291.29 joules. Units of heat are joules, and the negative just means that the heat was released. We're not going to worry about significant figures yet because we're not ultimately finished with the problem. So this concept, not really an equation, but this concept comes into play. The Q gained by something needs to be lost by something else. And we're assuming, and this goes back to what assumptions are being made, we're assuming that we have no heat loss, that it's a perfect transfer of heat energy. There's no heat loss to the environment, for example. So here, the Q of the aluminum is going to be equal to the opposite value of the Q of the water. So the Q lost by the aluminum is going to be equal to the Q gained by the water. So we already know this, meaning the Q gained by water is just going to be the opposite. So that's going to be positive 1,291.29 joules. And then if I do it in a different color and we go back to the water, we know the mass of the water, we know the final temperature of the water, we know the specific heat of the water. And at this point, we also know the Q of the water. So the last thing to find is the initial temperature of the water. We have 4 out of the 5 variables. We can solve for the 5th one. So we have solved for the change in temperature of the water. Notice that here there is a positive sign because that's the amount of energy that was gained by the water. It's only going to be a negative sign up here when we're talking about the aluminum. And we put in the specific heat of the water and the mass of the water. So we have a delta T of 6.178 degrees Celsius. Now I'm not paying attention to sig figs, we're just carrying out a bunch of them. So then to find the initial temperature, and you can do these calculations together, but I just separated them. We have one more calculation that we have to do. So the final temperature was 26.5 minus the change we just saw. And we're going to get a difference here of to only 2 sig figs and no decimal places because our temperature up here didn't have any decimal places. We'll do an initial temperature of 20 degrees Celsius. So don't freak out about sig figs on here. So that's the final answer. So an alternate way of doing this is just to take MC delta T of the aluminum and set it equal to the opposite of mc delta T of the water. And you actually do, you never actually have to find the Q value in that case, but you have all but one of the variables. So either way is acceptable. I just chose to do it in steps, but you can certainly do it in one shot if you set those equal to one another.